All right, let's look at another graph problem, building team. So what's going on here? We have n pupils and there are m friendships, and we are supposed to divide them into two teams, and we don't want to have any friends on the same team. And it doesn't matter how big they are. I suppose actually you could have one team with everyone, potentially, if no one had any friends. It would be very sad, but it's the degenerate solution. Anyway, so we're just given, the number of people and the friendships. And we're supposed to output, one or two for each person, depending on which team they assigned, or impossible, if it's impossible. So this is basically asking for a two coloring of the graph, right? So sometimes people like to think about coloring graphs, and usually the idea is that you want to assign colors to each vertex such that each edge has two different colors on the endpoints. In this case, each friendship has different teams with two people. By the way, how can it be impossible? Well, for example, if we had A is friends with B and three people basically who are all friends with each other. If we had this, then it's impossible, right? Because if like A is 1, then B and C would have to be 2, but then B and C are in conflict. And it will turn out that if there's any odd cycle, right, that is, so this is a 3 cycle, a 5 cycle would be 5 edges. That's 6 edges, I can't count. Would be 5 edges, right? Because this would have to be a 1, and then this would have to be a 2, and then a 1, and then a 2, and then a 1, but the 1's conflict. So if you have any odd length path like this in the graph, then that's a problem, and it will turn out that that's the only problem. So how do you do this? It's basically greedy, I guess, kind of. So you pick any random vertex, you assign it color 1, and then all of its children you assign 2, and all of their children you assign 1, and all of their children you assign 2, and so on. And if you ever get a conflict, right, if this 2 connects back to this 2, then it's impossible, right? There's a 3 cycle, 1, 2, 3. And if you have multiple components in the graph, assigning the 1 here might not be enough to sort of fix everything. So you might find another vertex that's undetermined after that, and you can just assign that one 1 and keep going. So that's basically it. It ends up being BFS, or I guess a series of BFSs right across each components. So the code for this is going to look very similar to like the counting component, like the first problem in this section. All right, so let's do it. And we'll do this one in Python. Yeah, so we just have a bunch of edges. One index, so we should change them to 0 index. And now we just want to go through. Right, so we're going to assign everything colors. Initially, everything is uncolored. So when we come across an uncolored vertex, we're going to do a BFS from it to color the whole component. And I suppose we should assign it a intended color. So if you come across an already colored vertex that's the wrong color, well, I should say, if we come across an already colored vertex, If it's the wrong color, that's bad. And we can stop now. We've already found out that it's impossible. If it's already colored and it's the right color, we don't need to do anything. You've already sort of seen that one. And all of its children. We can just add to the queue. And we want to add things even if we've already checked them before, because we need to check that there's no color clash. And if you've already colored them, then we won't do anything. Right? It's only in this case that we haven't colored it already that we actually do something. We just want to swap between 1 and 2. So 3 minus 1 is 2, 3 minus 2 is 1. And we just want to print the space-separated list of colors, assuming that we never hit a contradiction. And let's just assert that we actually got everything. Yeah, so append wants a pair, and also here. Okay, 1, 2, 2, 1, 2. That is the same thing that they got. Of course, there are multiple answers. Building teams. Cool, so this worked. Yeah, so we just go through all the vertices. If it's not colored yet, that means that it starts a new component. So we do the BFS to color in this component. So initially we'll just color, the starting vertex 1. Could be 2, that doesn't matter. And then for everything that we're exploring, if we've already colored it, we don't need to do anything cursively, right? We've already explored the neighbors. We just need to check that it matches. If we haven't already colored it, then color it that color and color each of its neighbors the opposite color. And yeah, that's it. Check that we hit everything, and then just print out the answer. And if we do run into a contradiction, then print out impossible. So, we don't even need to know that like odd cycles make it impossible or anything like that to solve this problem, but that is true. Phi coloring the graph, by the way, is a much, it's like NP complete. It's a much harder problem. 2 coloring is like linear time. Is there anything else to say? No, not really. That's the problem.